Okay guys, welcome back. So this is the second part of the videos on mechanics. So actually I explained to you about the forces and the types of forces, the tension in the first part of this video. So the second part of this video, as I explained to you in the last video, I will explain about the some special occasions in which different forces are used. So one of the special occasions in which forces are used is the concept of apparent weight in a lift. Now you may experience this already, but it's evident that if you keep some balance on you and then experience this force, so if you have some balance or something like this, so that it reads your weight, so when the lift is at rest, you can say that the normal force exerted on this man is equal to the mass times the gravitational acceleration or the weight of the weight of this man. So at that instance, the apparent weight equals true weight. So what is apparent weight? Apparent weight is the value of n. Apparent weight is actually the normal force. So that is the force that is experienced by the weight. So weight experienced by the scale. So if you measure the reading of the scale, you will feel that mg is equal to n. So when mg is not equal to n, you will experience the reading of the scale not to be mg but to be n. So what happens when the lift accelerates upwards? So when the lift accelerates upwards, so what generally happens is that the normal force is in the upward direction, mg is downward direction, so the total net force on this object is n minus mg, and that is equal to m times a because the lift accelerates upwards. So n equals m times g plus a. So you know that n now is, since a is greater than 0, you can say that n is greater than mg, so the apparent weight is more than the true weight. A contrasting occurs when the lift accelerates downwards. When the lift accelerates downwards, mg is downwards but n is upwards. So by applying F equals ma for the man, you can say that mg minus n is equal to m times a because the acceleration is downwards. So n is equal to m times g minus a. Since a is greater than 0, you can say that n is smaller than mg now. So the apparent weight or the reading of the scale is less than the true weight. But although a should be greater than 0, a should be smaller than g. So a should vary between 0 and g. Now in this case, what happens when a is equal to g? Now I explained to you that when a is less than g but greater than 0, n is less than mg. Now when a is equal to g, what generally happens here is that g minus g becomes 0. So we call that the person is in free fall because n is 0, the apparent weight is 0, or the person is in free fall. So that's it about the apparent weight, the variation of the apparent weight on different acceleration environments, and also even though the acceleration is same, when the acceleration direction is different, you may feel different readings of the scale. So another occasion where these special forces come into play is the contact force, or when the masses are in contact. Now when these two masses are in contact, you can see here that if the mass capital M and simple m are in contact, this mass exerts a force on this mass. So that's actually the contact force, and according to Newton's third law, this mass exerts a force on this mass. So those two forces should be equal because they are Newton's third law pairs. So these two forces are equal. So by applying F equals ma either for the whole system or by to the systems individually, you can find that the force is equal to the sum of masses times the acceleration, and thus the acceleration is equal to force over the sum of the masses. So both of these forces are internal forces. So this internal force retards this object because the applied force is in this direction and the internal force is in this direction. So this force acts so as to hinder this force, so as to oppose this force. But this force, the force exerted by the larger mass on the smaller mass, is in the direction of F. So this favors the motion and thus accelerates the object. And I explained to you this in the concept of the first video as well, in the concepts that I explained on the first video as well, about the division of, actually the decomposition of forces and finding the acceleration. So if you have some mass on an inclined plane like this, and its inclination is theta, you can say that the weight acts directly downwards in the direction of the gravitational acceleration, but the normal force is not parallel or linear with the mg or the weight of this object. It's always perpendicular to this surface. So when you decompose mg in perpendicular directions, you can obtain mg sin theta down the inclined plane and mg cos theta perpendicular to the plane. Now this object doesn't move in this either in this direction or in this direction, so r should be equal to mg cos theta, and the only force that acts downwards to down the plane is mg sin theta, and that mg sin theta should be equal to the mass times the acceleration. So a is equal to g sin theta. And what happens when there's friction? When there's friction, you can say that you can still find r equals mg cos theta, because mg cos theta is the only value that is in this direction. So r equals mg cos theta. However, you know that at the limiting occasion of friction, f equals mu r. So r is mg cos theta, so you can substitute for r. So f equals mu mg cos theta. So what is the acceleration of this object? To find the acceleration, you need to apply f equals ma to this object. So by applying f equals ma in the direction that is parallel to the inclination of this surface, you can say that the two forces that act on this object in this direction are mg sin theta and mu r. So mu r is actually mu mg cos theta here. So mg sin theta is in the direction in which we take, so it is positive mg sin theta. However, mu r or f or mu mg cos theta is in the direction that is opposite to the direction in which we consider. So that is mu mg cos theta, and that's minus, so we subtract that. So mg sin theta minus mu mg cos theta makes it mass times the acceleration. You can cancel m off because it's not equal to 0. So finally the acceleration is as follows. Another occasion where some special forces come into play is the flying of birds. When a bird flies, now it's not the concept that happens when an aeroplane goes on. However, when a bird flies, what happens is that it displaces the air below the wings. The force due to the change of momentum is the force given to the air by the wings of the bird. Now the weight of this object, weight of this bird is acting downwards, and the velocity of displacing air is also downwards. So the force or the air drag, the drag of this bird is in the upward direction. So if f is greater than mg, so the total force in this direction is positive, so the bird flies up. Similarly, if f equals mg, the total net force is 0, so the object or the bird doesn't move. If f is less than mg or mg is greater than f, the total net force is in this direction, so it should fly down. If v is the speed of the bird, the distance it travels within a unit amount of time is also v. So the volume of air displaced by the bird within a unit time is a times v, because you know that the distance moved within a unit time is v. Volume is equal to distance or the length times the area. So the area, if the area of this wing, if its wings area is a, you can say that the volume of air displaced, this volume v, this one is equal to a times v. Now you know that the mass is equal to density times volume. So m equals rho av, because volume equals av, and force equals rate of change of momentum. So momentum is mass times the velocity, so that is mv over 1, rate of change of momentum, and finally the force is given as rho av squared. Another application and the final application that I'll be talking about in this video is the movement of a bicycle. When a bicycle is moving in some direction, now you see if this bicycle is moving in this direction, the wheel should turn in this direction like this. So this wheel makes a friction in this direction, and this wheel makes a friction in this direction. First, a friction occurs when the wheel tries to move backward relative to the earth. So the wheel tries to move backward relative to the earth here, and the friction is in this direction. Then due to this force F1, the body moves forward, which causes the front wheels to develop a force F2, frictional force here. So first of all, now when this wheel is trying to move, when you rotate this pedal, what happens is this wheel tries to rotate here, so the wheel tries to go in this direction. So in this direction, if the velocity is in this direction, so the wheel tries to move in this direction, so the frictional force is acting so as to hinder the motion, and this frictional force causes the object to move. And then when the system is moving, because this is a complete system, when the system is moving, this wheel also tends to move in this direction, so the frictional force on this wheel acts in this direction. So the frictional forces are in opposite direction, although it's on the same system. When applying brakes, it's completely opposite. This wheel turns in this direction, so when its velocity decreases, its friction is in this direction, and again the friction of this wheel is already in this direction, so the frictions now are in the same direction. Now what happens to the momentum or the speed when an object changes? Only the momentum or the speed of an object changes only when an external unbalanced force acts on it. Now what happens when this person lands on this object and when this person gets away from this object? Now when this person lands on this object, the initial velocity is u, and if you think that the final velocity is v, and the mass of the trolley is m, and the mass of this man is m, capital M. Now when this man falls on this object, there's a friction between these two surfaces, because this is a rough surface here. So the man exerts a pressure, actually a friction on this object in this direction so as to hinder its motion, and due to the Newton's third law, you know that the friction on this man will be in this direction. So the man accelerates and this object decelerates. Finally they come to a common velocity. So although when considered as a whole, there is no unbalanced force. The frictional force which acts on the trolley decelerates the trolley, while the frictional force that acts on the object or acts on this man accelerates that object. So you can say that mu is equal to m plus m times v, because the total frictional force is 0, right? So the total net force is 0. So you can apply the conservation of linear momentum to find the final velocity. So final velocity will be equal to the mass of the trolley multiplied by the initial velocity of the trolley over the mass of the man and the trolley combined. And when the person leaves this trolley perpendicularly while the trolley is moving, what happens is, now you can say that when this person moves, if you take the initial velocity to be v, u, and the final velocity to be v, you can say from the principle of cohesion that mu plus capital mu is equal to capital mu plus mv. So you can say that u equals v. Thus the speed is unaffected when there is no frictional force acting in both directions. So that's about the conservation